Hello, welcome to our talk about using the Rust programming language to minimize the environmental impact of IT. My name is Shane Miller, and I lead the Rust open source team at AWS. I am also the chairwoman of the Rust Foundation. I'm joined today by Carl Lurch. Carl is a prominent member of the Rust community. He's the author of Tokyo, the leader of the Tokyo core team, and he's a principal engineer on the AWS Rust team. Carl and I are going to walk you through the evolution of energy efficiency in the cloud. We're going to talk about differences and energy efficiencies in different programming languages. We'll share some success stories from Rust customers, and we will reveal the secret sauce that makes Rust unique. We'll give you what you need to get started with Rust, and then I'll close with some of my thoughts about the future of Rust. So let's begin by looking at energy consumption across data centers. Worldwide, data centers consume roughly 200 terawatt hours of energy each year. That's 1% of global energy use. That's a lot, and as we look at this graph, there's something else that's interesting here. The graph is showing us energy use since 2010, and what we can see is that the distribution has been largely uniform. That is, the amount of energy data centers have been consuming worldwide has been largely unchanged for more than a decade. That's amazing, right? It's counterintuitive because we know we've seen explosions in things like big data, machine learning, edge devices. So what's the explanation for it? Well, as we look inside the rectangle, what we see is that the distribution across traditional cloud and hyperscale data centers has changed dramatically over that time. And what we're doing when we migrate to cloud and hyperscale is we are adopting energy efficiencies, right? So it's the energy efficiency gains in our data centers that have balanced the growth in our storage and compute workloads. What are those efficiency gains? There are far too many for us to cover in the talk, but let's go through just a few examples. We have computation reductions. Those are things like processor improvement efficiencies, but also smarter use of our servers, smarter utilization of our actual servers that decrease the idle time of our boxes. Storage reductions, driver density and efficiency improvements. We've reduced the growth of our servers through features like multi-instance and multi-tenant. And then our data centers have shown improvements in things from building materials to cooling systems. All right, that's a great story, right? Came to a great sustainability talk. We have huge growth, and that's being balanced by efficiency gains, and we have been doing that for over a decade. So then the question is whether or not it's enough, right? Can we continue to balance the growth in the future? And is it enough just to balance? Do we need to do better? Is 1% of worldwide energy being consumed by data centers where we want to be? I say probably not. I think that the explosion of edge devices is going to continue to grow the amount of data we're consuming, the amount of data we're processing, and the machine learning algorithms that are learning from that data and delivering on the innovations we're so excited about. So what else can we do? Well, we've talked so far about cloud infrastructure energy improvements. But in the same way that security is a shared responsibility, sustainability is a shared responsibility model for AWS as well. AWS customers have responsibility for data storage policies, for software design, for utilization that is energy conscious. AWS owns the things that we've talked about earlier in this talk, right? We talked about hardware improvements, building material improvements, cooling system improvements. That's where AWS has responsibility. AWS is also making a lot of investments in renewable energy. In fact, AWS is on the path to power all of our operations with 100% renewable energy by 2025. But even renewables have an environmental impact. To get the 200 terawatt hours that our data centers need worldwide will take 500,000 acres of solar panels. The environmental impact of mining, manufacturing, and managing all those panels is substantial. Well, we're really proud of the success we've had with our renewable energy. As Senior Vice President Peter DeSantis said last year at reInvent, the greenest energy is the energy we don't use. Renewables cannot replace energy efficiency as a design principle. In the same way that operational excellence, security, reliability, extensibility are traditional software design principles, sustainability must be a design principle of modern software design. What does that look like in practice? Well, relaxing SLAs for non-critical functions. Where we can, we should optimize on resource efficiency. Allow for longer device upgrade cycles. We can use virtualization to extend the life of our laptops and our edge devices, using caching and extending our TTLs whenever possible. Classify our data and implement automated lifecycle policies that delete that data as soon as possible. And finally, choose efficient algorithms for things like cryptography and compression. Last but not least, implement software in energy efficient programming languages. There's an amazing study that was done a couple of years ago, and it was looking at the correlation between energy use, performance, and memory consumption. This is a topic that comes up a lot in sustainability because we want to know what metrics do we already have today that we can leverage as proxies for energy consumption. For example, can I look at my infrastructure costs or my performance graphs and then make inferences about my energy use based on those trends? And how strong an inference can I make? So the study measured execution time, energy consumption, and peak memory usage for 10 benchmark problems that were implemented in 27 different languages. And here are the results. C and Rust significantly outperform other languages in energy efficiency. In fact, they're 50% more energy efficient than Java, 98% more energy efficient than Python. Let's take a moment to absorb that. It's not going to surprise anyone that C and Rust are more energy efficient than other languages. It's the magnitude of the difference that is really impressive. Broad adoption of C or Rust would reduce energy consumption of compute by 50%, even with conservative estimates. So why don't you C? We have a lot of C programmers. During his keynote at Open Source Summit earlier this year, Linus Torvald acknowledged that implementing code in C is comparable to juggling chainsaws. A lifelong C programmer, Torvald knows C's subtle type interactions are not always logical and are pitfalls for pretty much anybody. Torvald called Rust the first language he saw that might actually be a solution. Rust delivers the energy efficiency of C without the risk of undefined behavior. We can cut energy use in half without losing the benefits of memory safety by writing our solutions in the Rust programming language. Several analyses have estimated that more than 70% of the high severity CVEs occurring in C and C++ code would be prevented by implementing those same solutions in Rust. That's table stakes. Rust combines the efficiency of C with the memory safety of Java. The Internet Security Research Group is an organization founded for the Let's Encrypt project. That's the nonprofit certificate authority that provides TLS certificates for 260 million websites. They have a goal to move all of the Internet's security sensitive infrastructure to Rust. And you can look at and read about their project on their website at memorysafety.org. The current projects include support for Rust in the Linux kernel and migrating the curl use of HTTP and TLS to Rust implementations. All right, let's go back to those results. Remember, I told you that this study was about looking at correlations between energy, performance, and memory. So the middle column on the same results that I showed you before is showing us execution time. What we're seeing is that you get the performance of C with Rust. That is, when you choose Rust for sustainability and security, you also get the performance of C. Tenable is a cybersecurity solutions provider focused on exposure visibility tools. And they had a sidecar agent that filtered out unnecessary metrics. It was written in JavaScript, and it was doing fine, performing perfectly in production. But as they started to scale, they experienced performance problems. So they decided to rewrite the JavaScript filter in another language, and they chose Rust for its performance and memory safety. These are the results. With their Rust implementation, they had 50% improvement in latency, both at the median and the P95. 50% performance improvement is great. That's great. But here's the thing, that's not all they saw. Tenable also saw a 75% reduction in CPU usage and a 95% reduction in memory usage in production. Look at those graphs. Look at those graphs. That is substantial savings. And again, that's not just dollars saved, that is energy saved. These are the graphs of an energy efficient, sustainable implementation. So what about Rust at AWS? Well, Rust has quickly become critical to building infrastructure at scale at AWS. Amazon's first notable product built with Rust, Firecracker, launched publicly in 2018. Firecracker provides the open source virtualization that powers AWS Lambda and other serverless offerings. At AWS, we use Rust to deliver products like Amazon S3, Amazon EC2, and Amazon CloudFront. Last year, we launched BottleRocket, a Linux-based container operating system written in Rust. And our Amazon EC2 team uses Rust as their language of choice for new AWS Nitro system components, including sensitive applications such as Nitro enclaves. At AWS, we believe leaders create more than they consume, and they always leave things better than they found them. In 2019, AWS became a proud sponsor of the Rust project, and in 2020, we started hiring maintainers and contributors to the Rust project and ecosystem, like Carl. In 2021, AWS partnered with Google, Mozilla, Microsoft, and Huawei to found the Rust Foundation, a nonprofit with the mission to support the Rust project and its maintainers. AWS is investing in the sustainability of the Rust project. And the Rust project is building a language that I believe we should build sustainable and secure solutions with. Here to talk more about the unique properties of Rust and lead us to the next steps is Tokyo author and core team leader and AWS principal engineer, Carl Lurch.
Thanks, Shane. Now, I've been using Rust for about 7 years, and I originally got involved because I thought it was a really promising technology, especially for writing networking services such as databases or proxies. So for the past 7 years or so, I have been using Rust, yet while I have obviously been aware of the performance advantages, I never considered using Rust as a sustainability tool because my intuition of the impact was that it would be tiny compared to other factors, such as fuel consumption. And it's only been recently that I learned that data centers account for over 1% of all global energy usage. That's a big number. That's the energy that is required to run software that we write as software engineers. So when I learned that, I realized how big of an impact we as software engineers could have, and that's also when Shane and I started to think about how we could use Rust to reduce carbon emissions. Now, Rust is already being used today to ship real-world software, but it isn't from the point of view to reduce carbon emissions. So I talk to developers every so often, and I like to ask them, why did you start using Rust? And by far the most common answer that I get back is some variant of the runtime performance. Whether it's because Rust is faster or Rust has more reliable tail latencies, it's almost always about performance. For example, Discord started as mostly a Python, Go, and Elixir shop. Now these are great technologies, but Discord had a problem. One of their key Go services was experiencing really bad tail latencies. Now, this was a pretty simple service. It was used to store and fetch small objects and also included an in-memory cache. Now, because Go is a garbage collected language, as objects are created and released, every so often the garbage collector needs to stop execution of the program and run a garbage collection pass. While the garbage collector is running, the process is unable to respond to requests. And that's what you can see on this graph. The spikes are when the garbage collector is running. Now, to fix this issue, Discord decided to try to rewrite the service in Rust. The service was small in terms of code size, so they took the opportunity to try out Rust and to see what would happen. And here are the results. On the left is the Go service, and on the right is the Rust service. Now, these graphs look similar, but check this out. They are actually using different units. The Rust version is more than 10 times faster overall, with the worst tail latencies being reduced 100 times. These are some really incredible gains. And because the server is able to respond to requests far more efficiently, fewer servers are needed, which in turn means less energy is used and less carbon is emitted. So while Discord didn't start out and decide to use Rust to reduce carbon emissions, reducing carbon emissions ended up being one of the outcomes. Now, of course, Rust isn't the first efficient language. C has been around for a long time. But Rust is the first mainstream programming language that is efficient without sacrificing safety. And that's important, especially when writing networking services. Again, 70% of all high-severity security vulnerabilities in software written with C and C++ are due to memory unsafety. So Rust gives you that efficiency without feeling like you are playing with fire. Now, of course, since C, there have been new programming languages. Java, you may be familiar with Java. Java came along and addressed the memory safety issue by automatically managing memory at runtime with a garbage collector. So garbage collectors track outstanding references to a piece of memory, and when all references go out of scope, the associated memory can be freed. So the garbage collector handles memory management for you. Now Rust, instead of using a garbage collector to maintain safety, Rust uses ownership and borrow checking. So ownership is a fairly simple concept, but it has deep implications for the rest of the programming language. So in Rust, every piece of memory is going to be owned by a single variable. So every bit of memory has an owner. And that owner is going to be responsible for tracking that memory. So there's going to only be one owner at a time, but the ownership of the data can be passed around. So let's look at an example. First, I want to show a little bit of code written with Go. Here is a message passing example. On one side, we create a gift, and then we send it via the channel. Then some other Go routine is going to receive the gift and then open it. So Go's garbage collector is going to manage the memory for us. However, in this snippet, we accidentally opened the gift after sending it into the channel. So the gift here is going to be opened twice, resulting in a bug. We open it on the sending half and open it on the receiving half. Unexpected behavior will happen at runtime. Now, here is the same message passing example with Rust. The gift is created and it's assigned. We say that the gift variable owns the data. Then ownership of the gift is passed into the channel. Then the channel consumer receives the gift and takes ownership of it. And because it takes ownership of the gift, it is able to open it. Now, if we try to open the gift after sending it into the channel here, the compiler is going to shout at us because we violate the ownership rules. So already we're seeing how Rust helps us prevent bugs. Now, because Rust enforces that only one variable owns the data, when that variable goes out of scope without passing off ownership, there is no more possible way for that data to be accessed. So Rust is going to automatically free the memory at that point. There's no need for us as software engineers to manually free the memory. The compiler does it for us at compile time, not at runtime. Now, Rust's ownership system is built into the type system. It's part of the type system. And it's based on a concept called affine types. An affine type imposes a rule that every variable is used at most once. So the key here is going to be to define what used means. For Rust, a use is either moving the data or dropping it. So by using affine types, the Rust compiler is able to reason about the program and enforce its ownership rules. So this affine type system used by Rust, it's based on work done starting in the early 90s. Some folks attempted to design a Lisp that worked without a garbage collector. They were successful, but they found that they lost a bunch of runtime performance due to excessive copying introduced by not being able to have multiple references to the same piece of data. So with a garbage collector in Lisp, you can have multiple outstanding references and the garbage collector tracks it. When they removed the garbage collector, only one owner required a lot of copying of data. And this gets us to the second innovation that has enabled Rust, the borrow checker. So when writing larger programs, we tend to use abstractions. It helps us organize ideas. And one abstraction you may have heard about is a function. I hope you use functions. Now, functions often require arguments. If we only had ownership to call a function, we would need to pass ownership of the data into the function. And then when the function is done, it would have to pass ownership of the data back when returning. This is going to require copying memory when calling the function and copying memory when returning. And that was that source of the runtime performance hits with the Lisp when the garbage collector was removed. So to solve this, Rust lets you borrow data. All right, if I have a gift, I own it. It's mine. Now, if Shane wants to admire that gift, she can. She can borrow it for a moment. I'll let her borrow it. But she has to give it back to me when she's done. Also, when Shane's borrowing the gift, I can't hand off that gift. I can't give that to someone else. Shane has it. She's borrowing it. Now, crucially, those rules, the borrowing rules, the Rust compiler is going to enforce them at compile time. So Shane can't just borrow the gift and run off with it. The Rust compiler says, no, you have to give it back. And because the Rust compiler enforces that guarantee at compile time, when borrowing data, memory doesn't have to be copied. The memory stays where it is, and then a pointer is passed around into functions. That pointer is guaranteed to be valid by the compiler, so we don't see bugs like use after free. So putting it all together, you have a system that is efficient and prevents bugs, especially as the program gets larger and more complex. So here's another example. Given a vector, we take a reference to the first element, we push in another element, we push it to the back of the vector, and then we're going to use that original reference. So when we use that reference, the vector is still in scope, and it holds the original elements being referenced, but Rust doesn't let you compile this. So I included the equivalent C++ version. That version does compile, but it's not going to execute as expected. So to understand why there's a bug, you have to understand the implementation details of the vector type. Vector allocates memory to store elements and guarantees that all elements are stored in contiguous memory. Vector also lets you push in new elements without having to specify the total number of elements that need to be stored. So to do this, the vector may need to grow its internal storage when a new element is pushed onto the end. When this happens, to uphold its guarantee of storing elements in contiguous memory, existing elements being stored will need to be moved. The vector is going to allocate new memory, move all the old elements to the new memory, then insert that new element to the end. Which means any reference taken before pushing that push call is going to become invalid. The elements are no longer there. They've been moved. So with C++, you just have to know this. You got to know it, and you have to make sure to not do the wrong thing. Don't do the wrong thing. With Rust, the program just doesn't compile, because if it were to compile, that would violate Rust's rules. All right. But wait, there is more. So it turns out that the same system that prevents memory unsafety can also prevent data races. So a data race is a category of concurrency bug. A data race happens when two or more threads are concurrently accessing the same data, and at least one of those accesses is a mutation. So concurrent reads with mutations, or two concurrent mutations. Now, the same type system, Rust type system, that can model ownership and borrowing is able to uphold those same guarantees across multiple threads. And those guarantees also will prevent the data races because you can't mutate while reading. Rust prevents that. And because Rust completely eliminates data races, a big category of concurrency bugs, we as software engineers are able to use concurrency without having to worry about those kinds of bugs. They just can't happen. It lets us take more advantage of concurrency. And this isn't an accident. It ties back to the story of Rust's origins. So Rust started as a research project within Mozilla. Mozilla is the maker of the Firefox browser, and browsers are both very performance sensitive and also our first line of defense against all the bad things that can happen on the internet. So consumers of browsers expect them to be fast. And one way to be fast is to use concurrency. Modern hardware, modern computers, modern laptops have many cores, and they can take advantage of concurrency. Yet, browsers have historically not done much with this because getting concurrency right in C++ is really, really hard to do. So Rust was a research project that aimed to solve this problem. And they did. In 2017, Firefox shipped Quantum, which included a pure Rust CSS engine that leverages concurrency. And with these changes, Firefox is able to render pages up to 80% faster. And now I want to show you how easy it can be to safely add concurrency to a Rust application. So here we have a function that iterates through an array of numbers, and it sums all even numbers. This is a highly parallelizable operation. And for very large arrays, we could see that function getting significantly faster by adding concurrency. So the left side here shows a single-threaded version, and the right side shows you the parallel version using the Rayon library. So look at how similar these functions are. You get all the power of concurrency without the hazards by basically writing the same code. So the only difference here is that we're using the pariter method instead of the iter method. So the parallel version will spread that computation across many threads, all while avoiding copying that original array of numbers that's passed in as an argument. And also, each thread is going to be able to access the different elements in the array with no synchronization because the checks happen at compile time. So Rayon is able to provide this API safely thanks to Rust's ownership and borrow checking system. Again, all the checks happen at compile time. At runtime, it's just pointers being passed around with no added synchronization. So hopefully by now I've gotten you interested in Rust and starting your journey of sustainability in the cloud. Okay, so where to start? Well, the good news is all the content you need to get started is available online for free, and here are the places to go to. So first thing, you'll need to learn Rust, the programming language, actually learn the programming language. And the Rust book found on the website is an excellent resource to get started learning the language. You'll learn the easy part, the beginner, like the basics, and then the Rust book is also going to teach you the more advanced parts of the language. All while starting by showing you how to get the tool chain installed. The website also has exercises and lots of code examples to read, so you can work through, get practice, and also see a wide range of Rust in real world usage. And if you get stuck at any point, have any questions, or need any clarification, you can post on the user forum or talk directly to the community on the community Discord server. So my preference is the Discord server. It's usually the fastest way to get help. There's almost always people there who are very active and friendly, and that real-time aspect is useful for working through problems. And once you've gone through the Rust website, you should already be getting comfortable enough with Rust to start building things. But here is another resource that I really want to call out. It's a great resource for doing deeper dives. So The Crust of Rust is a YouTube channel by John Jensett, and he does really in-depth videos on Rust topics. Now, he really pops up the hood, explains how things work, and his videos, they're usually multiple hours long, and I think recently he even posted a 7-hour long video. So you gotta carve out some time or break it up, but I hear constantly from people how valuable these videos are to help them understand Rust and get familiar with Rust. Also, if you're at reInvent, John is here as well. So we'll be at the booth. Well, I'll be at the booth too. So come and say hi. Now, once you've learned the foundations of Rust, if writing network services is your thing, I would suggest going to the Tokio website. So Tokio is a library for writing asynchronous network clients and servers. And I am the lead of the Tokio project, so I may be a bit biased, but I think the website has a really good tutorial to get you introduced to asynchronous Rust with Tokio. And it does this by walking you through implementing an incomplete version of the Redis key value store, both a client and the server. And there are also lots of examples to read, including the final mini Redis implementation. We also have our own Discord server, which is quite active and a great place for asking questions and getting help. So for implementing networking services, the Tokio website will be your best starting point. And also at reInvent, we have OPN 304, a workshop that introduces you to asynchronous Rust. It's going to be led by Felix, a member of the Rust language team, and John of Crust of Rust is also going to be there. So if you want a hands-on workshop to get started, come to OPN 304. It's Tuesday and Thursday. Okay, so I've been talking about how awesome Rust is, how Rust enables you to write efficient software without sacrificing safety. How you can use Rust to write network services, and how you can trivially parallelize your code in ways that were not super easy before. And we're also, we're seeing Rust adoption take off. Within Amazon, more and more teams are picking it up because of these advantages. And outside of Amazon too, excitement is growing. I keep hearing how new orgs are having success deploying Rust software. Again, even the Linux kernel is looking to add support for Rust. We're writing modules. Linus Torvalds, known for his dedication to C, again described Rust as the first language he saw that might actually be a solution when talking about memory safety. So does that mean Rust has made it? Because if we are going to reach those carbon reduction goals that Shane spoke about, we are going to have to, if we're going to reduce energy usage in the data center by 50%, we are going to need to see most new software written in energy efficient languages like Rust. So are we on track for that? And now we get to the elephant in the room, Rust's learning curve. Rust's learning curve is notorious. So perhaps you already have been reading up about Rust, and you might have come across articles that include bits like, Rust can be difficult and frustrating to learn. Or, perhaps you were on a forum and saw a post that included something like, I, a beginner, am getting frustrated with Rust's learning curve. These are some common themes that come up. Based on survey data, the perceived time to be productive with Rust is between 3 and 6 months. That's a good deal higher than other programming languages. And that cost results in developers stalling or abandoning Rust at the implementation step. Now, clearly everyone isn't bouncing off. Rust usage is growing significantly, but we aren't seeing Rust being adopted everywhere. What we are seeing is that Rust is really taking off in spaces that can really use Rust's efficiency. So high volume data plane services, databases, distributed systems, or smaller like embedded in IoT where you have really small hardware. We aren't seeing big adoption across all backend services like backends to JavaScript apps, just those cases that are really negatively impacted by a garbage collector. So what are we going to do about it? Well, I'm going to hand it back off to Shane, who is going to talk a bit about our plans and how we're going to be addressing that cost of adopting Rust.
So I started this talk from the perspective of my position as a leader of the Rust open source team at AWS. And I'd like to finish the talk from the perspective of my position as the chairwoman of the Rust Foundation. The Rust programming language delivers the performance and resource efficiency of C with the memory safety of a garbage collection language like Java. And the Rust developer community, they have a few sayings that try to capture this intersection of two amazing attributes. They say things like, have your cake and eat it too, or performance, reliability, productivity, pick 3. Rust promises to deliver on a lot of dimensions. Let's take a closer look at that last one. Performance. Okay, so we talked about the results from an experiment that indicated that, that demonstrated that performance of Rust is comparable to C. We looked at customer success stories that showed tremendous performance gains from implementing their services in Rust. Check, we've got performance. Reliability, we've talked about the memory safety and the concurrency safety of Rust. We've also talked about how we get consistent performance in the long tail at the P99. Reliability, check. Productivity. Well, Carl just talked to us a little bit about the learning curve with Rust. Maybe we should take a closer look at productivity. Of the more than 8,000 developers who responded to the 2020 Rust user survey, only 100 of them identified as expert. And of the engineers who are no longer using Rust, 55% cited productivity and learning as their reason for abandoning the language. Experienced engineers require 3 to 6 months of study with access to subject matter experts like Carl in order to become productive using Rust. Some engineers have likened learning Rust to learning to eat your vegetables. Once they get started with it, once they get productive with it, a lot of them love it. But also, a lot of engineers are deciding not to learn Rust or are abandoning the effort before they're productive. The potential impact of Rust on sustainability and security is only going to be realized if we turn the broccoli into a brownie. No one developer, service, or corporation can have a material impact on sustainability. Energy efficiency best practices are like recycling. They only have impact if we all do them. If we're going to have an environmental impact with Rust, we need to grow the developer community. And the Rust developer community is growing. It's the fastest growing developer community for the last 2 years. But as you can see from this graph, we are far from the widespread usage needed for real change. And we also know that based on historical trends, that of the 500,000 developers that joined the Rust community in the last 12 months, few of them are likely productive with the language. So we have some work to do on the Rust developer experience. But which Rust developer experience, right? One developer's ideal experience is another's nightmare. The differences between what is an ideal experience for a Linux kernel developer, for an S3 developer, for a website developer are substantial. So AWS researchers are working to identify the Rust user personas by distinguishing those users across 3 different dimensions. One, we're looking at reasons for using Rust. Is the engineer coming to Rust to solve a security problem? Are they coming for because they're building a critical system that is going to depend on the security features of Rust? Or are they coming for performance? What domain is the engineer working in? Are they in embedded services that are resource constrained? Are they working with machine learning? They have huge amounts of data. And then 3, the developer's background. Are they coming from a systems programming background, or is their experience with only with dynamically typed languages? We want to evolve these combinations of priority, domain, and developer experience into more robust understanding, a common vocabulary, and an explicit set of trade-offs. For example, we may identify a security-focused persona that builds, for example, cryptographic implementations. I like to give my personas names, and I always start with Bob. So let's pick on Bob. Poor Bob, he is a security engineer, and he is prioritizing security over things like performance and operations. What does that mean? It means that Bob would rather wait longer for a response than receive plain text. It means that Bob would rather experience an outage than an unsigned request. For each of these personas, there are going to be different engineering trade-offs, and we need to empower them all to build the best solution for their persona without getting into conflicts with one another. So what does that look like in practice? Well, what we have today is what's in the green box. Down in the corner, we have the Rust project with the language and the compiler and some relatively small developer tools for things like package management and a small core standard library. We also have Rust projects like the one that Carl has created and leads today, Tokyo. We need to create a platform, more platforms like Carl's Tokyo, for common language, scaffolding, developer tools, and documentation, and for many more use cases. So what's the moral of the story? Rust is an amazing technology to secure and sustain our industry. You can start using Rust and make a difference today. Rust does have a lot of work to do before everyone can use it, and the Rust Foundation is working to create the platform for people across our industry to effectively collaborate on Rust. So if this is the kind of thing that interests you, please get involved. We would love to have you contribute to building this vision. It's open source and it takes people to build it. There are a bunch of people from the Rust community who are here this week. We'll be at the open source booth, and we have an EBC that you can sign up for. Get involved. Let's build technology and community that outlast us all. Thank you for your time today. I hope we've given you something that's valuable.